Okay, hello. In this video, I'm going to introduce you to a rule that's going to be handy from time to time. Let m be a positive number. Let a, b, and c be real numbers such that a is less than c which is less than b. Excuse me. And let d be a subset of the reals such that d is a superset of this interval right here. And again, c may or may not be an element of d. Okay. And let f be a function from d to r such that the limit x goes to c of f of x equals 0. And let g be a function from d to r such that negative m is less than g of x, which is less than m for all x in d. Then it's going to follow that the limit as x goes to c of f of x times g of x equals 0. And notice, guys, in this definition, let's look at what we said. M is a positive. Now, C may or may not be in D, but that doesn't matter anyway, whether it is or whether it isn't. And even if it is, F may not even behave there, even if C is in D, which is the domain of F. Again, C is, of course, not in this rightmost guy by definition. This is the deleted closed interval. Okay, so, well, what's going on here? F is tending to 0 as x goes to c. Now g is bounded. G will never, in absolute value, the absolute value of g will never go above m because g never goes more negative than negative m, and it never goes more positive than positive m. So g is what we call bounded. It's caged between negative m and m. It's squeezed. Now the limit as x goes to c of g of x, it might or might not necessarily exist. We don't necessarily promise that the g limit even exists. It could, but it doesn't have to. Well, but g state is caged in between these, but the f limit does exist and it equals 0, so the limit of this product is actually going to equal 0 because g can only do so much damage. He can only hold f back so long because he's caged between these values. He's caged. G cannot, well, let me put it this way. A minute ago when I said G can't go above absolute M, I really should have said the absolute value of G of X can't go above the absolute value of M for any X in our domain. There we go. So G can only do so much damage, so this limit is still 0. G can slow F down. This limit right here, like G it can speed F up, which is all the merrier. It can slow F down, but it can only slow F down so much. At the end of the day, this product is going to go to 0 in any event. Now, for all we know, M could be a trillion, but M is finite, so there's only so much damage that G can do. So here's an example. Let g be a function on the closed interval from 1/2 to 5 into the reals, such that g of x equals 12 if x is rational, and g of x equals -3 if x is irrational. So g is not a nice function at all. In fact, no limit, if c is any number, the limit x goes to c of g of x will not exist. G is, it's not infinite at all, but notice that doesn't mean it's pretty. G is a very weird function. It just doesn't get big. Let f be a function, on the other hand, from 1/2 to 5 into the reals. I keep forgetting my codomains on these. Sorry, bad habit. So let f be a function from 1/2 to 5 into the reals such that f of x equals x minus 1 for all real x. And that's for all x. Okay, and I really should say, to be good-mannered, in the reals. But anyway, it's been difficult, but anyway, for all real x. So let's just put it like that. Sorry for the delay there, guys. So for all real x. Okay, so notice that, now I just picked, 13 is not sacred. You could pick 14 or 15. I picked 13. G of x is caged between -13 and +13. You could just as well say -14 to 14, but anyway. Now, you do have to be careful. You do have to go above 12. You could say 12.001. You can't use 12 itself or anything below 12. Like pick 12.1 or 13 or 14 or whatever. G is caged between -13 and 13 or -14 and 14 or -12.1 to +12.1 Now, since g is caged between negative 13 and 13 for all x in this interval, after all, g is either negative 3 or it's 12, so it's obviously never going to get outside of the open interval neg 13 to pos 13. Okay, for all x in this closed interval, g satisfies this, and since this is true, the limit x goes to 1 of f of x equals 0, total continuity for f, right? Not for g, but for f, we have total continuity. F of the limit x goes to 1 of f of x is f of 1, which is 1 minus 1, which is 0. So that by continuity, so we have that. We conclude from the above rule that the limit as x goes to 1 of f of x g of x equals 0. Now, up here now f was pretty nice. I picked a very nice f. I didn't necessarily promise that f of c even existed up here, let alone continuity at c. I didn't promise any of that up here. But down here, I picked something that was more than sufficient. I picked an f that was just pretty, okay? Up here, there's a little more leeway that we have. We're obligated for the limit to exist at c of f of x, but we're not obligated for f to be continuous at c. F doesn't have to be completely nice. It just has to be nice enough for this limit to exist at c. Okay, but anyway, let's look at another example. Let g be a function from 1/2 to 5 into r such that g of x equals 12 if x is rational and g of x equals negative 3 otherwise. So g is the same as it was before by definition. And let f be a function from, again, I forgot my codomain. Sorry about that, guys. I'm just getting silly here. Oops. Okay, so there's my codomain. Sorry about that. Sorry for the pause. Okay, so f is this function such that f of x equals x minus 1. Then we have, if I do the product, now that's interesting. If I do f times g, I'm going to look at things from a different angle. Sort of a similar idea, but from a different angle. Like, we considered the product up here, and we know by the rule up here that this limit is 0. So I didn't finish. Let me go back up here and finish what I started. So since this is 0, we conclude from the above rule that the limit of this product is 0. Sorry, I moved on to the next example before I finish this one. So g is caged, the f limit exists, and it equals 0. So this limit right here of the product exists and equals 0, even though the individual g limit itself does not exist. So sorry about that. I almost moved on to the next example too quickly. Now let's move on to the next example. So let g be this function, same function, and let f be the same function. Let's look at the product. The function f times g, such that f of x times g of x is going to equal 12 times x minus 1 if x is rational, and it's going to equal, let's see here. Oops, I made a mistake. That 5 should be a negative 3. Sorry about that. Because g is negative 3 if we're irrational. But in either event, f of x, g of x is caged between neg 13 absolute x minus 1 and pos 13 absolute x minus 1 for all x in this closed interval. And furthermore, the limit as x goes to 1 of these two extremes, this left extreme here and this right extreme here, their limit is going to tend to 0. Hey, by the squeeze theorem, the limit of this guy in the middle would have to be 0. Oh, okay. That's from the squeeze theorem point of view. So that's pretty cool. But can you appreciate why the above rule? Notice that rule that I gave, but notice that this rule was this was a little messy here, and can you appreciate why the rule would save some time? Don't worry too much about that, but I just wanted to show you, it can be inconvenient to appeal to the chain rule sometimes. The rule, when I used it the first time, made things clean. That's all I'm saying here. Maybe a little bit cleaner. Not, the chain rule wasn't just bad, but, we saved a little time by using that rule. let's move on. Let f be a function from r to r such that this is the case right here for all x and r. Notice that we don't even know what f looks like in concrete terms. Then by the squeeze theorem, the limit x goes to 0 of f of x equals 0, because this guy right here goes to 0 as x tends to 0, and so does this guy. So this guy in the middle would have to tend to 0 by the squeeze theorem. One choice for f, f could be a lot of things. One possibility for f would be, let's just say f of x equals x. Like x would go beautifully right here where my cursor is. But f of x doesn't have to be x. F of x could be a lot of things. It could be a little on the strange side, but it behaves. And so we have otherwise. Indeed, hey, you know what? Another choice for f would be the very strange function f of x equals x if x is rational, but f of x equals 0 if x is irrational. That function is strange. But hey, it's also caged on this interval right here. That's nice. It would be, we can put it right here too. And by the squeeze theorem, now you remember early in this class, we just took it for granted that limit existed and equals 0 just by visual consideration. Now by the squeeze theorem, it's true. So we have a little more hard evidence. We can appeal to the squeeze theorem. Now, of course, this function is not continuous anywhere else. At any non-zero point, that strange function right here is discontinuous at any non-zero point. It's only continuous at 0. Okay. Now, if we tried to mess things up and cause trouble, if we did not define f of 0 to be 0, let's say we go up and tweak the definition such that f of 0 is either undefined or it equals something that is not 0. Let's say that f of any rational is 0. Let's say that the definition is still the same, but let's change f of 0 to be something else. Or we could just change it to be undefined. Then we would ruin continuity. The limit would still be 0, but continuity would be lost. So if we messed up f of 0, we would lose continuity, but we still would not lose the limit. The limit would be fine. If I defined f of 0 to be a billion, or if I left f of 0 to be undefined, the limit would still exist, but I would ruin continuity. Okay. Now, the next thing I do is just review examples. And I think these would be better saved for the next video. Thank you guys. I'll close out this video.